Howdy. Salutations. Buenos dias. Good morning. Whoops, she showed up again. Hello, Sea Dog. I wrote your recommendation the other day. Muy bien. ¿Y usted? Let's see. We got 21 viewers. 22. 22 viewers. I don't know how to say viewers, but nosotros tenemos 24 viewers. Okay. I'm going to go ahead and get started. Okay. So today, we are going to talk about the drag force. Espectador. Okay. Nosotros tenemos 25 espectadores. Hang on, I have to add that to mi cuaderno de español. Espectadores. Los espectadores son los viewers. Okay. Got distracted there. Okay. So we are talking about the drag force today. All right. This lesson is necessarily going to have some calculus in it that you may or may not know yet. That's okay. I'm going to box some equations. Those are the equations that you are going to use. Okay, so if you don't follow the calculus, that's okay. You're just going to write down the equations that are boxed in. Okay, it's not necessary for the AP exam or the IB exam, but I'm going to include it anyways because it's important. Okay, so drag force. Drag force is the force of air resistance. Okay? And so there are a number of different models for the drag force. Okay? There's a model for the drag force called Stokes Drag. Okay? And Stokes Drag says that the drag force is minus a constant times the velocity. So the drag force points in the opposite direction of the velocity, and it is linearly dependent on the velocity, okay? So it's an oppositional force, and it is linearly dependent on the velocity. This constant K, it's a constant that depends on two things. It depends on the shape of the object that is moving through the fluid. So objects that are more aerodynamic or hydrodynamic or whatever are going to have a smaller K constant. They experience less drag because they're better at, so less of a resistance force for moving through a fluid, okay? The other thing it depends on is the fluid itself. How viscous is the fluid that the object is going through? So if you're moving through outer space, K is 0 because outer space has no drag, right? Or very, 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 very little drag. You know, you might bump into a few atoms here and there that slow you down, but for the most part, there's no drag. If you were traveling through air, the K constant might be smaller than it would be if you were traveling through water. Okay? So the K constant for air is different from the K constant for water, even if you had two objects of the same shape. If you were traveling through molasses or some thick fluid, then the K constant is going to be very large. Okay? So it depends on the shape of the object, and it depends on the fluid. Stokes drag is the model of the drag force that is used in the AP exam. Okay, so that's the model that we're going to study the most. But it turns out that it is only appropriate for very small objects, and when I say small objects, I mean like bacteria, so really small objects, or slow things. Okay? So you have to be going really slow or be really small in order for the drag force to be modeled by this kind of a... But like I said, this is the model that the AP exam uses because it is easier mathematically. It's an easier introduction to drag force. A more realistic model is you say that the drag force is equal to a constant times the speed squared. This is more appropriate to a wider range of situations. So things like airplanes have a drag force that depends quadratically on the speed. So for Stokes drag, if you double the speed, you double the drag force because it's linearly dependent on V. For this form of drag, which I'm just going to call drag, it depends quadratically on the velocity. So if you double the velocity, you quadruple the drag force. Okay? So it's a different model. But we're not going to use this one in this class. At least not until after the AP exam. If I decide to do a more advanced version of this lesson, then I would probably bring that in. Okay, so the first case I want to consider is motion through a fluid with no gravity. Okay, so that's the first case that we're going to consider today. So basically, when would you move through a fluid with there being no gravity? If you were in outer space and you were coasting through a cloud, a nebula, like a dense nebula, then as you're cruising through the nebula, you're going to be bumping into the molecules within the nebula, and that's going to slow you down. It's going to create a drag force. Okay, so we have no gravity. So that means that the only force is going to be the drag force. Okay, only force is going to be the drag force. So let's write Newton's second law for this example. Net force equals m times a. All right. The net force is the drag force. Okay. Because that's the only force. Then the mass is m. And I'm going to write the acceleration as the derivative of the velocity. Okay. So this type of an equation is what is called a differential equation. Okay. As opposed to an algebraic equation. An algebraic equation is one where to solve it, you just sort of move the variables around so that, you know, velocity is on one side, for example. And then you have the velocity. But here, it's an equation for velocity that includes the derivative of the velocity. So we can't just solve this equation by rearranging variables. In order to solve the equation, we're going to have to do derivatives or integrals or something like that. So it's going to have, so that's called a differential equation, okay? And what you want to do to solve a differential equation, see, we're looking for the velocity as a function of time, okay? And so when you have a differential equation, what you want to try to do is you want to try to separate the variables. Okay? You're going to separate the variables. Okay? So separating the variables. What does that mean? We're going to have anything with v on the right-hand side of the equation. Actually, let's say the left-hand side. Anything with t on the right-hand side. And the constants, it doesn't really matter. Okay? So what I'm going to do is I'm going to divide both sides by velocity. So I have minus k equals m times 1 over v dv dt. Okay? So I have velocity all on this side of the equation. Okay? Because I have dv and v on the right-hand side. But I need to put time on the other side, so I'm going to multiply both sides by dt. Okay? And I can see that because I multiplied the right-hand side by dt, the dt's will cancel out here. So I have m dv over v. And I have minus k dt. All right. Now I said I'm going to put velocity on the left-hand side. So I'm just going to reverse the equation, right? If a equals b, then b equals a. So I have m dv over v equals minus k dt. I'm going to divide both sides by m. So I have dv over v equals minus k over m dt. All right? So this is a separated differential equation because the two variables, velocity and time, are on opposite sides. I don't have velocity on this side. I don't have time on that side. So they're separate on separate sides of the equation. Once you separate the variables, what you want to do is you want to integrate both sides. And this is the part where if you are just taking calculus for the first time, or maybe you're not taking calculus at all, this is the part that you're not going to get. That's okay. All right. So I'm going to integrate both sides. Okay. And on the left-hand side, I'm going to on the right-hand side, I'm going to integrate from 0 to t. And on the right-hand side, I'm going to integrate from v initial to v. Okay? So you might recall from your calculus class that the integral of dx over x is natural log of x. There is an absolute value in there, but we don't really worry about that too often in physics. So on the left-hand side, I have natural log of v minus natural log of v initial. Okay? And on the right-hand side, k and m don't depend on t, so I just have minus k over m times the time elapsed. Okay? All right. Now, when I subtract logarithms, that's the same thing as dividing the arguments. So I get natural log of v over v naught equals minus k over m times t. I'm going to take the exponential of both sides. So if I do e to both sides, the e cancels out the natural log. So going to the other side, I get v over v naught equals e to the minus k t over m. And then I multiply both sides by v, and I get, or by v naught, excuse me, and I get that v of t equals v naught e to the minus kt over m. So this is the equation that we want to get to. All right. So this is what you would box in if you have not taken calculus or you have not gotten to integration yet in your calculus class. So the key takeaway, key observation, is that drag causes an exponential decay of the velocity to 0. Okay? If you were in outer space coasting through a nebula, eventually the drag force would slow you to a stop. It would take an incredibly long time because, nebulas, generally speaking, are not very dense. But if you entered the nebula, it would ever so slowly bring you to a stop. If we were to graph the velocity as a function of time, okay, it looks like an exponential decay. So you start out with some initial velocity, and it slowly goes to 0, like this. Okay? Exponential decay. Asymptotically approaches 0. Notice the bigger the mass is, see how mass is in the denominator there? The bigger the mass is, the more time it's going to take to slow to a stop. Okay? This is borne out by this equation. So if you have a large mass, it's going to take a longer time for that velocity to go to 0. Okay? The bigger the mass is, the longer time it takes to come to a stop. That's because more mass means more inertia. The bigger the k constant is, remember, a big k constant means that you're not very aerodynamic. So the bigger your k constant is, the more significant drag is, and so you're going to slow to a stop more quickly. Okay? So it might do something like this. So K and M determine how quickly this exponential decay happens. All right? Okay, so we're going to go to step 2, which is what if we have drag force with gravity. Drag force with gravity. So that means we're going to have two forces. We're going to have the weight force and we're going to have the drag force simultaneously. Okay? For this example, we are going to choose downward is positive. Okay? So, starting with net force equals MA. There are two forces acting on this thing. Okay, it's falling, so it has weight force going down, and it has drag force going up. All right. So our net force is going to be mg minus kv. All right. Remember, I am choosing downward to be positive. Okay. Downward to be positive. If the velocity is positive, meaning that it's going downward, then the drag force is going to point upward. It's going to be oppositional. That's why there's this minus sign there. Okay. So this is the differential equation in the presence of gravity. Okay. You should be able to write this equation down and understand what each of the terms means. So even if you can't solve the equation because you're not there in your math understanding, you should be able to write this equation down. Now, one of the phenomenons that this equation has is it has the phenomenon of terminal velocity. Okay, so what's going to happen as this thing falls is it's going to pick up more and more speed. And as it picks up speed, the drag force gets bigger and bigger. And eventually we have a situation where the drag force is balanced by the weight force. And in that case, the object stops accelerating. Okay? So if you have an atmosphere, when something falls, it reaches a maximum falling speed, which is called the terminal velocity, and that occurs when the drag force balances the weight force. So you've acquired so much speed that the drag force is equal to your weight force, and you're not going to accelerate anymore. Okay, so we can calculate the terminal velocity. Okay? Here's how we calculate the terminal velocity. The terminal velocity is achieved once the acceleration equals 0. So we just plug in 0 into this equation for the acceleration. So we have mg minus kv equals 0. All right? Then we can notice how this became an algebraic equation now. It's not a differential equation anymore. It's an algebraic equation. So we add kv to the other side, and we divide both sides by k, and we get v equals mg over k. So I will call this combination, mg over k, I will call that v sub t for the terminal velocity. Okay? So we can see that after a long time, this is the speed that the object will have. Okay? All right. So this equation makes a lot of sense if you think about it, because the more massive the object is, the more inertia it has, the harder it is to slow it down. So the more massive something is, the greater its terminal velocity. The stronger gravity is, the more significant the weight force is in pulling the object towards Earth. So the bigger the acceleration due to gravity, the larger the terminal velocity. The bigger the k constant is, the less aerodynamic the object is, or the thicker the atmosphere is. So the bigger the k constant is, the smaller the terminal velocity is. If you're less aerodynamic, you're not going to fall as quickly. Okay? So this equation makes perfect sense to me. All right. So now we got to solve this this differential equation. Okay? So what I'm going to do is I'm going to divide both sides by k. So I have mg over k minus v equals m over k dv dt. All right? So now I'm going to separate variables. And so to separate variables, I'm going to divide both sides by mg over k minus v. All right? And so this cancels out, and I just get 1 on the left-hand side. Okay. And then what I'm going to do is I'm going to multiply both sides by minus k dt over m. So I multiply by minus k dt over m. The m cancels out with that m. The k cancels out with that k. The dt cancels out with that dt. And all I have to do is worry about that minus sign, which I will multiply into here. So on the right-hand side, I have dv over v minus mg over k. So that minus sign reversed the order of the two terms. And then on the left-hand side, I have minus k dt over m. I'm going to go ahead and replace this term with v sub t for terminal velocity, because that's the terminal velocity. All right? So this is actually dv over v minus v sub t for terminal velocity. So I have separated this equation because I have velocities on the right-hand side and I have time on the left-hand side. There's no time. This t stands for terminal, so I have no time on the right-hand side. I have no velocity on the left-hand side. Once you've separated your equation, you want to integrate both sides. Okay? So I'm on the left-hand side, I'm integrating from 0 to time t. And I'm going to assume that at time 0, the velocity is 0. So that means we have released this thing from rest. Okay? From 0 to v. Okay? So if I do the left-hand side, and this middle one gets integrated too, but we don't care about that. Integrating the right-hand side, I get natural log of v minus vt evaluated at v and evaluated at 0. Okay? On the right-hand side, or on the left-hand side, I have minus kt over m. So doing the subtraction, which is actually division, on the right-hand side, I get natural log of 1 minus v over vt. Okay. So now I'm going to do e to both sides. Once again, the e is going to get rid of the exponential. Okay. Or is going to get rid of the natural log. So I have e to the minus kt over m equals 1 minus v over vt. And we're trying to solve for the velocity now. So what I'm going to do is I'm going to add this term to the other side. I'm going to subtract the exponential term. And then I'm going to multiply both sides by v sub t, the terminal velocity. So we have v sub t times the quantity 1 minus e to the minus kt over m. Boom! There you have it. That is the velocity as a function of time. So how is this different from the case with no gravity? Well, when we have gravity, your velocity time graph is going to actually look like this. This starts at rest. So we start out with a velocity of 0. And it's going to build up to the terminal velocity. Okay? So after a long time, the velocity approaches the terminal velocity. Okay? You know what? Why don't we plug this into Desmos? Okay, I'm going to plug this into Desmos, this function into Desmos. So what if I typed in, I have to call it y, I guess. Y equals, can I call it v? V of t equals 5t, does that work? Oh, it does it, okay. So this equals 5 times the quantity 1 minus e to the negative t. Okay, and this is only defined for t greater than 0. So we can see that we have a sort of exponential approach to the terminal velocity. So notice how 5 is the overall multiplying factor, so that means that the terminal velocity is 5, and we can see that this asymptotically approaches 5, right? If I put in v equals 5 in there, we can see that asymptotically we are approaching the value 5. Okay? So, all right, class, that is my lesson for today. And so I will see you in the Zoom room in about 2 minutes. Okay? Bye now.